David Smith here with another Flipped Classroom math video. A few tips before we get started. Remember, you can always pause the video if you need to catch up with your notes. You can also speed up or slow down the playback if that helps. Finally, you can turn on the captions so you can see my words going by at the bottom of your screen. Okay, today's lesson talks about linear models, and it's the first of 4 lessons in a series. So we're just going to develop this idea of linear models. So before we start, a couple things. Linear means line. So these are models that represent relationships that make straight lines on the graph, and we'll get to that in a minute. Models are mathematical equations that represent relationships. So with this example, it's purely mathematical, but there are linear models that express ideas that exist out in reality, like in our last lesson where we talked about a motorcycle losing value over time. So let's get started. So linear equations, which is where most of us come from in this concept, could be written as f of x equals mx plus b. Hopefully this is feeling familiar, this mx plus b part, but we'll explain it anyway. F of x equals mx plus b is pretty much the same as saying y equals mx plus b. Remember, when we talked about functions, f of x is just another way of saying y. Okay, so just remember that those are interchangeable. Okay, so in this equation, the m stands for the slope of that linear equation, which is the rate of change in the relationship between x and y. The b is the y-intercept. That's where that equation crosses the y-axis, and that's where x equals 0. So we could write at x equals 0 for greater clarification. So that b, whatever that number is, the point 0b, is the y-intercept. Okay? So that's the basics of linear equations. Let's just take a look at a couple equations and how they show up on the graph. So here's an example one. F of x equals 2x plus 1. So the slope is 2. M equals 2. And the y-intercept is the point 0, 1. So let's put this on the graph. Now the easiest way to do that with when it's in this mx plus b form is to first graph the y-intercept. So that would be 0, 1. That point is right there. And then use the slope to find another point. So slope of 2, or slope is rise over run. So this is 2 over 1. So that means go up 2 and over 1, both in the positive direction, as there's no negatives there. So we go up 2 over 1, and that's going to be our next point. And then we can just draw our line right through there. And this is the line y equals 2x plus 1. Or we could write f of x equals 2x plus 1. So what I'd like you to do now is pause the video and graph this function. Notice how this one is listed as f of x, this one is g of x. We can use any letter in front of the of x that we want. But when we have a situation that has more than one function, then we make sure we use different letters for each function. So go ahead and put g of x equals minus 3x plus 2 on the graph. Okay, let's see how you did. Actually, before that, I'm going to correct one thing. Since we do have 2 functions on this graph, we are going to use f of x for this one, and we'll use g of x for the next one. Okay, so m equals minus 3, that's my slope, and my y-intercept is going to be 0, 2. Okay, so now I can go to 0, 2. Actually, I'm going to grab a different color for clarity's sake. 0, 2 is this point. Then my slope is negative 3 over 1. So now, instead of going up 3, remember rise over run, I'm going to go down 3, 1, 2, 3, and over 1. And that will be that point. So this line looks like that, and this is g of x equals minus 3x plus 2. So there's a quick review of the basic form of linear equations, pulling out the required information, the slope and the y-intercept, a couple examples, and how they look on the graph. This should be review for you. If you feel like you need more, just let me know. I have tons of videos that talk just about this. Okay, let's take a closer look at that slope, the m, the slope, which we're going to really jump into what it means to be a rate of change. So here is kind of a wordy definition of the rate of change. Let's go over it. It's the increase or decrease in the dependent variable, which is y or f of x. So it's the increase or decrease in the dependent variable for every 1 unit of the independent variable. Okay? So every time the independent variable changes by 1 unit, how much change do we get in the independent variable? Okay? So that's a little bit abstract. Let's take a look at an example of a rate and tease that out a little bit more. So here's speed. We're going to use metric. This is 50 k per hour. I should say km because that's the official abbreviation for kilometers. So 50 kilometers per hour, that's a rate. That's a rate of change. That's speed, which is, actually pause the video for a minute. Which two quantities are we measuring with this? We know the units of them, kilometers and hours, but what are those quantities? So think about that for a minute. Okay, so let's see how you did. We're measuring distance, that's one of our quantities, and time is the other one. So now think about that for a minute and tell me which one of these is independent and which one is dependent. We've got time and distance. Okay, so if you thought time was independent, you're correct. And so that means distance is the dependent variable. Now remember, time is almost always the independent variable. There are very few situations where time is actually dependent on something else. Okay, so now that we know this, let's look back at our definition. It's the increase or decrease in the dependent variable, which is distance, for every 1 unit of the independent variable. And this makes sense. So pause the video for a sec. What is the unit of the independent variable? Look at this section right there. What's the unit? It's 1 hour. And this rate is saying for every 1 hour, "50 kilometers of distance is accrued." I might have spelled that wrong, but I'm not an English teacher, so I hope you'll forgive me. So, here we go. Increase or decrease in dependent variable for every 1 unit of the independent variable. So in this case, 50 kilometers per hour, our 1 unit is an hour, 1 hour. And our dependent variable is the kilometers. So this rate of speed means that for every 1 hour, 1 unit of independent, we get 50 kilometers and change in the distance the dependent variable accrued. Okay, so let's do an IB type word problem that puts all this together and actually gives you a little bit more. So let's take a look at the situation. We've got some kind of chemistry experiment, mad scientist in the lab bubbling and making stuff. The experiment lasts 8 minutes. There's a liquid that's heated and its temperature rises at a constant rate. So before we go on, constant rate is going to mean it's a linear situation. The rate is not increasing or decreasing, it's constant. So this is your clue that this is a linear situation, or there's a linear function somewhere behind this situation here. So temperature rises at a constant rate. The initial temperature is 40 degrees Celsius, and the final temperature is 320 degrees Celsius. So our situation is we're bubbling away some fluid. It starts at 40 degrees, it increases temperature at a constant rate, and 8 minutes later it's at 320 degrees. Okay, so that's our situation. First thing, list the independent and dependent variables. And notice how I said list. List is that IB keyword that means you can just do that without calculating. So think about that. Pause the video. And hopefully you remembered that time is almost always independent. So time is here and temperature is the dependent variable. And this makes sense because the temperature of the liquid is a function of how much time it has been heating. So the temperature depends on the time. So you can always make that connection with your words. Okay, next question. List 2 points on the graph of this situation. So presumably we could make a graph that shows the temperature as a function of time. Be some graph like this. Temp, time, and since it's going up, it would look something like that. Okay? So that's a really rough graph. It makes sense. The more... What did I do wrong? It goes like that. So as time increases, we're heating all that time, the temperature is going to increase, so the line is going to slope upward. It's going to have a positive slope. Okay, list 2 points on the graph. Pause the video for a second, see if you can figure out, it's all up in here, what those 2 points are. Okay, let's see how you did. The first point is we're starting at 40 degrees Celsius and we're at 0 time. So we could write 0, 40. Now, if you couldn't get that one, now you should be able to get the second one. So pause the video and jot that down. Okay, let's see how you did. So, and the experiment lasts 8 minutes, and at the end of the experiment, 8 minutes later, it's at 320 degrees. So we go 8, 3, 2, 0. So those are the 2 points on the graph. Now, if you're going to be fun with your graph, what you would do is you'd put 40 there, and then that's 8, and this would be 320. Now, the graph is still a little crude, but I put 2 points on there that are indeed accurate. Okay, here's the first tricky question. What is the rate of change? In other words, how fast is this liquid heating? If we could figure that out, then we could tell, well, what was the temperature at, let's say, we went 8 minutes, at 3 minutes, or at 7 minutes, and we could figure that out. But first, we need to know what the rate is. Now, the rate is the slope of this line. And you have to remember your line equation slope formula, which is this. M equals y2 minus y1 over x2 minus x1. That's the formula for slope between 2 points, x1, y1, and x2, y2. So these are 2 coordinate points. You measure the slope by just subtracting the second y, or the first y from the second y, divide that by subtracting the first x from the second x. So having this, and actually having that right there, there's your 2 points you need, you can calculate the slope. So go ahead and pause the video and do that. Okay, let's see how you did. My first step is a pure plug-in step. Don't do anything in your head, just plug the values in. Here's my m. It's y2 minus y1, y2 minus y1, 320 minus 40, over x2 minus x1. There's x2 minus x1, which is 8 minus 0. Okay, that simplifies down to 280 over 8, which then comes out to be 35. Now, 35 is not a rate. 35 is just a number. You've got to express your rates in a change in 1 unit per units of the other one. So in this case, the change is 35 degrees per minute. Okay? So that's our rate of change. One last question on our chemistry experiment. So I summarized the results so far. I erased the whole problem, but we know we have an 8-minute experiment. We know that at the start, at time t equals 0, the temperature is 40 degrees, and after 8 minutes, the temperature is 320 degrees. And then we used this information to find out that the rate of change is 35 degrees per minute. Okay? So that's where we are so far with this problem. Now let's take a look. Here's a question that's like a really nice summary question. You're going to see this type of question a lot. You're basically being asked to come up with a formula or come up with a function that relates time to temperature. So here we go. They're telling you what your variables are. Big T is temperature, little t is time. Go ahead and pause the video and see if you can write this in function notation. Let's see how you did. So let's write our function. It's going to be temperature as a function of time. T of t, a little confusing. However, that's fine. Now, I'm going to take a little side trip here. Here's our mx plus b. This function is going to be in this format, okay? So Temperature is a function of time. Time is our variable, so we're going to have it to be m times t plus b. So that's going to be where we plug the seconds in, where they would be x, but now it's going to be t. And then we need our rate. So what's our rate here? Our rate is 35. So we're going to write 35t. Now we have our b. So what's our b in this case? It's the y-intercept. So remember that graph we made? The temperature at time 0, it's 40 degrees. Time 0 is where this function is crossing the y-axis. Remember, this is y and that's x. So the y-intercept is this point, 0, 40. So what we're going to do is we're just going to add the 40 right there. So slope, rate of change, y-intercept. And we could test this out by plugging in 8 for t, and it should give you 320 for the temperature. And if you test that, you'll find that that indeed is true. Okay, let's do one more. Slightly different scenario, a little bit of a different entry point, but the same kind of problem. So we've got a water tank, and it empties. Someone pulls the drain plug at the bottom. It empties at a constant rate. It contains 930 liters 3.5 minutes after it starts to drain. So you don't know how much was there at first, but we just know that after 3.5 minutes it's got 930 liters. Then after 50 minutes the tank is empty. Okay, so after, what is it? It contains 930 after 3.5, and then it's empty after 50 minutes. Use W for the amount of water and T for the minutes after start. So let's answer all the same questions. Which one is independent and which one is dependent? Okay? Time, independent. Amount of water, dependent. Good. Name 2 points on this function. So we have the point 3.5, 930. That's after 3.5 minutes, it's got 930 meters, or liters. And then the other point is 50. After 50 minutes, it's got nothing in it. So there's our 2 points. Rate of change is going to be the slope between these 2 points. So y2 is going to be 0 minus 930, y1, over x2, 50 minus 3.5. If you do the math on that, this is minus 20 liters per minute. Okay? So there we have that. Now we need to come up with our equation. So now that we know our slope, we can write this equation. Water level as a function of time equals minus 20t plus b. Now we don't know our y-intercept, which is actually the amount of water in the tank when we start. But fortunately we know some things. When the tank is empty, this level is 0, it's minus 20 times 50 plus b, right? So minus 20 times 50 is what? It's 1,000, right? 1,000. Negative 1,000 plus b equals 0. So we'll move the 1,000 over. 1,000 equals b. So that's how much water is in at the very beginning. So our function is water level as a function of time equals minus 20t plus 1,000. Now check this out. Answer this question. Why is this rate negative? The temperature one, the rate was positive. Why is this negative? It's because the tank is draining. The water level is decreasing, so we have a negative rate, and our slope would be something like this. Our graph would look like this, whereas this is time, that's water level. Here's 1,000. Here we are at 50 minutes later with nothing in it. So it's downward sloping, just like you would expect with a negative rate. Now that you've watched the video, take a moment and write down any questions that you might have so you can bring them to our next class. Remember that you can always watch the video again and perfect your notes. Finally, if you enjoyed the video, please click the like button down below. And if you'd like to help me grow my YouTube channel, please click subscribe.